Okay, I guess it's 5 past the hour, so we can
Okay.
start. So welcome everyone. Thanks for joining. This is going to be our last meeting of the year. And today we're very happy to have Saurabhchand Bhati to talk about segmental contrastive predictive coding. And Saurabh is a PhD student currently at Johns Hopkins University, supervised by Najim Dehak. And yeah, so Saurabh, the floor is yours. Take it away.
Hi. Yeah, I'll share my screen. Hey, I hope everyone can see my screen.
Yep.
Okay. So yeah, I'm Saurabh. I'm a fourth year PhD student at CLSP Johns Hopkins. As I already said, I work with Dr. Najim Dehak, and I'll be talking about segmental contrastive predictive coding today, and we mainly use it for acoustic segmentation at both phone level and word level, and I'll go through how it's done and what makes it different from the other existing techniques. So first, I'll start with zero resource speech processing, and zero resource speech processing generally refers to an area or like unsupervised learning where you have minimal or no transcriptions that available to you, and unsupervised discovery of spoken terms or UTD is a very common task. That's the core task of zero resource speech processing, and it refers to as finding the repeated speech fragments. It can be done at phone level or word level. If you try to do repeating phone fragments, it's generally called as unsupervised acoustic unit discovery. If you try to do it at word level, it's called unsupervised word discovery. But both of these methods, they rely heavily on segmenting the speech into phone-like or word-like units. And for the remainder of the talk, when I say phone segmentation, word segmentation, I mean phone-like segmentation and word-like segmentation. We are attempting to divide the speech into phone-like units, but it not always resembles phone units. Oh, sorry. Yeah. And so the traditional method or the current methods for phone segmentation, they try to define the task of phone segmentation as boundary classification at each time step. So for example, you can have an RNN which tries to predict the next frame from the previous frame. And if you have a higher than a predefined threshold, then you define it as a boundary. Or you could track the forget gate in a LSTM, and whenever the norm of the forget gate is higher than a predefined threshold, you classify it as a boundary. So typically you try to define phone segmentation as boundary classification at each time step. And as for word segmentation relies on the intuition or the idea that word boundaries are a subset of phone boundaries. You can't have a word boundary if there's no phone boundary. So for word segmentation methods, you start from initial segmentation, which is initial segmentation can be phone-like or syllable-like, and then you iteratively merge the initial segments to come up at higher word-like units. But the limitation of this approaches or these approaches is the initial boundaries are typically fixed and they don't change during the word segmentation process. And there have been works which show that the quality of the initial boundaries dictate the final word performance, which makes sense as they are not being fixed; they are only being merged to come at higher level units. And so that's the limitation of these two methods. They are approaching phone segmentation and word segmentation by different methods, and even if when they are trying to use phone segmentation as a starter for word segmentation, it's not fully utilizing as the boundaries remain fixed. And another thing is you can also use word segmentation to improve phone segmentation. So these are some of the limitations that these current methods are not fully utilizing the interdependence. And that's what the main aim of this project was. Can we have a method that can do phone segmentation and word segmentation simultaneously and try to use the interdependence of the two tasks to benefit both of them, that is improve phone segmentation and word segmentation simultaneously. So before that, how any of it's done, let's take phone segmentation as an example. And if you look at just the raw speech waveform, includes information about a lot of things like identity of phone, speaker, language, and emotion. And if you have if you extract features like MFCCs or spectrogram features. All of these have been used for ASR, speaker identification, and all of these things. But so that means the traditional features are capturing information about all these sources of information. What happens is in a supervised scenario, you have a DNN which can extract the meaningful information out of these speech waveform or the MFCC features and just ignore all the irrelevant information. For example, if you were trying to do ASR on top of, say, directly speech waveform or MFCCs, it will try to map the features into a space which only keeps the phone identity information and ignores or tries to ignore all the speaker information or emotion information. And if you were to use the same MFCCs with the speaker labels, the features will now try to focus more on the speaker information, and they will try to ignore the text information when you're trying to do text independent speaker information. So in a supervised scenario, you have the advantages of having labels, which can help you ignore or select the information which you need and ignore everything else. But in a unsupervised scenario, you do not have labels which can guide you to relevant features. So a good feature representation is almost as good as having a good method, and it can improve the performance of unsupervised methods. So for example, if you were trying to do phone segmentation, and if your features already capture the phone class information more than, say, speaker or emotion, then it will be better for the segmentation method, or the segmentation performance will be better. So it's a good idea in general to have good features or that learn task specific information. And recently that has been the trend. People typically first learn representations and then they are passed into for unsupervised tasks like phone segmentation, word segmentation, or term discovery. And contrastive predictive coding and other self-supervised methods have been center of like representation learning recently. And CPC essentially learns features in an unsupervised manner, and it tries to do so by solving an auxiliary task of predicting the next frame. And to predict the next frame, you do not need any labels. As long as you have the unsupervised data, you know what the next frame is going to be, or next two frames are going to be. And then you can condition your model to learn the structure of speech data by solving such a task. And CPC has been used for speech recognition, speaker recognition, and it tends to capture the phone information really, really well. And now recently there have been approaches which use CPC for speaker identification or other self-supervised methods like Dino for speaker identification. And this is the CPC architecture. You start from a raw waveform, and the raw waveform is fed into this convolutional encoder, which typically downsamples speech by a factor of 160, same as the MFCC features, to extract these frame level features, ZT. These are extracted every 10 milliseconds typically. And these are then passed through a recurrent or a context encoder, which captures the context from these frame level encoders. Now the task for CPC is, given the context representation at time t, you try to predict the next frame ZT plus 1. And why just predict the next frame? People have extended to predict much farther into the future. And now you can try to predict ZT plus 1 from CT, ZT2 plus ZT plus 2 from CT, and so on. And the farther you predict into the future, generally tends to capture better representation up to a point, and after which the performance starts to degrade. And to improve the learning process, they not only simply predict the next frame, they try to predict the next frame from a bag of negative examples. So to sort of make the regression problem into a classification problem. And now from this bag, you have to predict which one is the correct one and the wrong one. And you could, in theory, do it as a regression problem where you're just trying to directly minimize the L2 loss between CT and ZT plus 1, for example. And this works really, really well for capturing the phone information from the unsupervised speech. And recently, it has been modified to do phone segmentation. And if you see, there are two main differences. The one difference is there is no context encoder in CPC for phone segmentation, and they are trying to minimize the loss between two frame level representations. And the objective for this kind of is, so you are essentially trying to predict the next frame from the previous frame, and you try to do so from a bag of negative examples. But now you don't have a context encoder, so you're trying to constrain the nearby frames to be as similar as possible. And the idea is, if you take two frames from one phone, they will be similar, and then you're trying to force them to be similar. And they learn the model, and during the inference, you can simply measure the dissimilarity scores between the current frame and the next frame, and that can be your score. And wherever you see a very low similarity, you can think of this as a segment change, or the phone information or the phone class information has changed. If you could predict the next frame very easily, then you are within the same frame. If you are having difficulty predicting the next frame, then it's likely that the segment has changed. So now the task of phone segmentation becomes finding these peaks or minimas, whichever way you define it. If you try to find the peaks in the similarity, then it's the task of peak finding. Or if you try to find minimas in similarity, then it's the task of minima finding. But now the task of phone segmentation is posed as finding these peaks in the dissimilarity value. And each peak is signifying where you have some sort of information change. And this information change refers to when the phone class information of the underlying features have changed. And so they generate these score vectors, or score vector for a utterance. And this is then passed into a peak detection algorithm, which will find the peaks into the algorithm. Sorry, peaks into the utterance, and the peak prominence threshold of the algorithm is tuned on a validation set. And this works really, really well for finding the peaks in the utterance, or finding the segment boundaries in the segment. But there's a limitation. CPC, or CPC for representation learning, or CPC for segmentation, they only look at the frame level structure of the speech signal, but the speech structure exists at multiple time scales. Like you can have, or if you look at the typical language models, they are at phone level, word level, or even at sentence level. And so our question was, what if we could leverage speech structure at multiple levels? For example, if we could look at not just the frame level, but also at phone level or even higher. And for this presentation, we are looking at how do we extract, or how do we learn from the speech structure at frame and phone level simultaneously, and does it help the learning process or not? And the next question is, what are some of the what are some of the challenges, and how do we include this multi-level structure into the learning process? First question is, when I say the phone language models, or the language models are at phone level, there we typically know what the phone boundaries are in a supervised scenario. But in an unsupervised scenario, we do not have access to the phone boundaries. And as like there have been a lot of work on identifying just the phone boundaries, and they're very difficult to identify correctly or as well as the supervised methods. So that is one of the problems. And even if we do somehow find the phone boundaries, different number of utterances are going to have different number of phones. And that's one problem. Another is phone lengths, even within an utterance, are going to be different. And it makes utilizing the phone boundaries in a batch manner really difficult. Within a batch, the data points should, or the model expects the data points to have similar lengths. So it makes the process of making batches from these utterances, which can have different number of segments. And not just that, each segment can have different length. And this is the main challenge that, these two are the main challenge that are stopping us from including the phone segmentation, or the phone information in the learning process. And we try to propose SCPC, which can model the speech structure at frame level and phone level simultaneously. And SCPC is a 3-stage hierarchical model, which is trained in an end-to-end manner. So we are trying to use the feedback from all 3 stages to train all of them. And the stage 1 of SCPC is a CNN, which learns the frame level representations from raw waveform. It essentially downsamples speech by a factor of 160 to RP to come at MFCC-like or representation. The second stage is a differentiable boundary detector, which takes in the frame level representations and finds the variable length segments from the utterances in a batch. And third stage is how do we use these segments to learn segment level representations, and how do we ensure that they are capturing the language model at phone level. So this is the SCPC architecture, and SCPC architecture stage 1. So we start from raw waveform, which are then fed into a frame level encoder, which is essentially a 6-layer CNN, which downsamples the speech progressively by a factor of 160, and to generate these frame level representations called Z. And at Z, we have this LNFC, which is the next frame classification loss. And here, what we are trying to do is, given a frame, try to classify the next frame. So for example, if I give you Z4, the task is to classify or to predict Z5 from a bag of, say, 2, which contains Z5 and Z8. So Z5 is the positive example, Z8 is the negative example, and our goal is to have the maximum similarity with the positive example. And this is the stage 2 of the architecture. In the stage 2, we have a differentiable boundary detector, which takes in the frame level features, and it generates this B vector, which essentially is a sequence of ones and zeros, and each one is indicating that a segment change has happened. So for example, if you look now, this method is generating the sequence of ones and zeros. First 4 frames belong to one segment, the next 2 from second one, next 3 from third one, and so on. So as you can see, the number of segments or the number of frames within each segment are different, and this is the entire architecture. So now we have stage 1, stage 2, stage 2 generating this sequence of stage 2 generating this sequence of ones and zeros. And now we have this segment representation step. For now, you can think of this as just the simple averaging operation. So it takes in the first 4 frame, takes the average, and generates the, let's call it the intermediate segment representation for now. And the reason why we do it to take care of the length issue. So now different number of segments have different frames, but if we take average or do some operation that is similar to averaging, it will generate a fixed dimensional representation for all the segments, regardless of the number of frames in the segment. So now for each of these segments, we generate a fixed dimensional representation, which is then passed into this segment encoder, which takes in for now the average and generates these segmental representations S. Now, if you ignore the bottom part and just look at the S and C, now what we are doing is we are essentially doing a CPC, but now it's operating at a segment level. And now the task at the third stage becomes predicting the next segment, for example, S3 given C2 from a bag that contains S3 and S4. So in this architecture, we start from, say, raw waveform. We had a downsampling by a factor of 160. Then we imposed a frame level loss, which generates the representation at frame level, which are then passed into a differentiable boundary detector, which generates the segment. And we did some kind of pooling operation, for example, average pooling, which generates same fixed dimensional representation for all the segments, regardless of their length. Now we can pass the averages through a segment encoder to generate segmental level representations, which are then passed through this context network, which works at now segment level instead of typical frame level. And then we have a next segment classification loss, which is essentially trying to predict the next segment given the past context. And now I'll go through the details of each stages. So stage 1 is next frame classifier. And in this stage, we essentially input the raw waveform and try to generate this frame level representation. And the objective is try to minimize or try to predict the next frame correctly from a bag that contains the next frame and a bunch of other negative examples. And for similarity measure, we are simply using the cosine similarity as for now. So this is the objective at the next stage 1 or NFC. The stage 2 is how do we detect these boundaries from a batch of utterances? And we follow the similar idea that height dissimilarity between successive frames is an indicator of segment change. And it follows the same assumption. If you could predict the next frame really well, then they are in the same phone class. And if you are having difficulty predicting the next frame, then that means the segment information has changed, and that might indicate a boundary between the current frame and the next frame. And so we first measure all the similarities between all the frames in an utterance. So ds is a vector that donates all the similarity between the current frame and the next frame. And if you look at dt, it's just capturing the similarity between zt and zt plus 1. And as if you remember, the similarity function is a cosine distance. So it's essentially a vector of cosine similarities between the next frame and the current frame. And it will have L minus 1 length if you have an utterance of length L. Now, to convert this into a vector of dissimilarities, we simply like 1 minus cosine similarity, but before subtracting it from 1, we normalize it by mean and max. So this will be between 0 and 1, and now the dissimilarity will be between 0 and 1. So it takes care of different amplitudes for different trenches and makes them sort of normalized. And now the peaks in this dissimilarity vector D will signify the phone boundaries. Now the task is, how do we find the peaks from this vector of dissimilarities? So to do that, we define these peak detectors, P1, P2, and P. And if you look at P, the tth entry of P is essentially this function. And let's break it down. If you look at the left part, this left part is essentially comparing dt plus 1 and dt. And if you remember, a peak is defined as if dt is higher than both t minus 1 and t plus 1. So if dt is higher than t plus 1, then this will be positive, and max of z positive, and 0 will be something positive. If dt is lower than this, then it'll be negative. So, and the right part is essentially comparing dt and dt minus 1. And if dt is greater than t minus 1, then I think there's a typo here. If dt is higher than dt minus 1, then this will be a positive entry and max of positive, and 0 will be something positive. So essentially what we have done is we have done a soft comparison. And if you were trying to do it outside a neural network, you could simply compare if dt is greater than both dt minus 1 and dt plus 1. If that's the case, then you have a peak. And if dt is less than either t minus 1 or t plus 1, then you don't have a peak. And instead of that, we are doing a soft comparison. If dt is essentially higher than t minus 1 and dt plus 1, then pt will be a non-negative positive entry. And if it's lower than either of them, then all of this will evaluate to 0. Now, just looking at t minus 1 and t plus 2, t minus 1 and t plus 1 to decide if there's a boundary or not might be noisy. So we repeat the same process, but instead of looking at just t minus 1 and t plus 1, we now look at t minus 2 and t plus 2. So the idea is the same. If we were doing it outside, we could simply compare dt with dt plus 2 and dt minus 2. Now we compare dt with dt plus 2 and dt minus 2, and this entire term will evaluate to something positive if dt is indeed greater than t minus 2 and t plus 2, and 0 if it's lower than either of them. And then we have this third equation, which is essentially combining the evidence from PT1 and PT2, and it basically combines them and checks if the PT1 and PT2 are more than this threshold, which this threshold is usually fixed. We can also learn it, and I'll talk about how the value of this particular threshold affects the final performance or the performance of both phone boundaries and word boundaries. So after that, essentially what we have is PT will be a vector of non-zero values if the model thinks there's a peak, and 0 if there is no peak. Yeah, so the vector P is essentially 0 at, this is the non-zero at boundaries and 0 everywhere else. And this is a typo. It's non-zero at boundaries and 0 everywhere else. But the non-zero values are going to be different across peaks, since we are subtracting dt from dt minus 1 and dt plus 2. And if you have higher or lower similarities, they're going to be different for different peaks. Now we just need a way to make them consistent to 1. And this is not helpful for detecting boundaries, as boundaries are already detected by P. It just helps us in the next process, which is generating the segment representation for all these variable length segments in a batch manner. So now we want to scale all of these non-zero values to 1. We could do this by multiplying this with a very large number, say 1000, and taking the 10 of this. If it's 0, 10,000 times, or 1000 times 0 is still 0, and 10h of 0 is 0. And if you have a non-zero value, for example, say 0.2, 1000 times 0.2 is 200, and 10h of 200 is essentially 1. So we could do that, but if we directly do it, then it will saturate all the gradients and the training will not be possible. So to avoid that, we use a straight through trick, which is essentially defining a soft boundary detector, which is you multiply p by a lower value, take the 10h, and then we define b hard, which is multiplying p with a very large value. So it will be a vector of zeros and ones. And the final b is defined as p soft plus top gradient of hard minus soft. So essentially what it's doing is doing the forward pass, the model sees the boundaries at zeros and 1, and in the backward pass, the model sees boundaries as whatever values they are. So you can train the frame encoder based on these similarity values or p values. So now that we have generated this vector of zeros and ones, we will go to the next step, but there are a few challenges that I talked about. The boundary detector can tackle all of them. We can find boundaries in a batch manner. Since we are defining b to be a 0 or 1 vector at each time step, it doesn't matter how many boundaries there are in the data, it will just change the size according to the utterances. And it does not require any constraints on segment length. You can think of this as being circumvented by the threshold value. If you use a very large threshold, then the segments will be very, very large. If you use a very small threshold, then the number of segments will be really, really large. But given a threshold, it does not require any constraints on segment length. And it can also detect the number of segments. We are not supplying it with any estimates or exact number of segments within an utterance or within a batch, and it is doing all of that automatically. Since all the definitions that we use for PT and PT plus 1, they can be scaled to matrix operations. So this can be done on a batch of utterances. So now we have a matrix B, which essentially contains zeros and ones for each utterance in a batch. Now this is the third step. So now what we have done is we have taken the features, our sequence of Z's, and passed them through the segmenter, and we have a sequence of segments S1 and S2 and SM. Now the objective is, how do we find the representations for these variable length segments? And for now, or for starting, we just chose average, since it doesn't matter how many frames you have within a segment, the average will be of same dimension. And you could do average, but if you try to do average segment by segment, it will be very, very slow, and the training of this model won't be feasible. So now the next step is, how do we compute a pooling or as simple as averaging on these segments which are of different lengths? So to do this, we define the spectralization trick, and I'll go through with it. Suppose you have the same vector B, which is a sequence of ones and zeros. Now we first generate or pass it through this cum sum operation, which is the cumulative sum from left to right, and generate this B modified vector. And if you look at it, it will have basically I if you are in the ith segment. And if you look at the first 4 frames, they are all ones, next 2 are all 2. So it will be I at ith location. And then we generate this mask matrix, which is of size L cross M, where L is the size of utterances and M is the number of segments within that batch. And you can find M by either taking the sum of B or the last index of this B modified. And each column of this U, which is the mask matrix, is I. So the first column is all entries of 1, the second column is all entries of 2. And if you remember the B modified vector, it is I, or the segment number at ith location. So if you subtract the 2, you will see something like this. All the places where you were in the first segment are 0 now, and wherever you are out of segment first, it will be something non-zero. And depending on If you subtract it before the segment, will be negative, and if you subtract it after the segment, will be positive. But the idea is by generating a mask, which is I in ith column, and generating this vector B modified, which is I at ith location. If you are in the ith segment, we can generate this mask matrix, which will be 0 if you are in the first segment, in the first column. It will be 0 in the second column, only at places which you were in the second segment. So it's 0 for first 4 in the first column, it's 0 for fifth and sixth. Now what we do is we need to just invert this metric. And to invert this metric, we use the same 10h scale, 10h trick. We multiply it with the scale. The scale is typically 5 for 5, and anything higher than that should work. We multiply this matrix, or the absolute of this matrix, with a scale which is 10. Take the 10h. What that does is it will generate all non-zero values to be constantly 1. And if subtracted from 1, it will generate a mask such that the zeros are now replaced by 1, and everything that was non-zero is now 0. And if you take the column-wise unit sum and normalize it across columns, it will generate a matrix which is 1 by 4, 1 by 4, 1 by 4 for the 4 entries in the first column, 1 by 2 in the fifth and sixth entry in the second column. Now what we have generated is a mask matrix, which is essentially 1 by the number of frames in a segment in that corresponding column. Now, if you want to take the average, you could simply multiply the sequences of feature vectors with this weight matrix or the mask matrix, and it will calculate the averages for you. And if you look at just the first column, we are essentially multiplying just the first 4 frames with 1 by 4, 1 by 4, 1 by 4, 1 by 4, and rest everything is 0. And this is essentially taking the average for us. And it does do a lot of redundant operations, but it is still much, much faster than trying to write a loop across the number of utterances in a batch and then all the segments on within an utterance. So, and this is essentially very fast to do on a GPU. So now we have a method that can compute or take care of the different number of segments within an utterance, and even for each segment, you have different lengths. So we can generate this 6-dimensional representation by multiplying with such a mask or weight matrix, and then we can pass the entire multiplication from the segment encoder to generate the segment level representations. And Z times W is just representing the averages of the segments. And now after this, now that we have generated the segment level representations, it's essentially a standard CPC. Now we have a RNN. In practice, I use a GRU as the recurrent neural network, which takes in the segment level representations and passes them through the GRU to generate this context level representations C. And now the task is given CT, you have to predict the next segment, which is ST plus 1 from a bag that contains or ST plus 1 and other negative examples. And you can choose the number of negative examples as your model dictates. And the model now has to minimize both the next frame loss and next classification loss. And by making the boundary detector differentiable, we are essentially allowing the model to optimize for both frame level structure and the segment level structure. And it can choose to focus on what's important, what's not automatically. And if you look at the learning process, the segment boundaries or the phone boundaries that do change during the learning process. And now that we have trained a model, how do you do any kind of inference from it? So if you want to do phone segmentation from SCPC, we generate the dissimilarity values at the frame level or between successive frames. So you will generate the same dissimilarity vector, but at frame level. If you are looking to do word segmentation, then we will generate the dissimilarity scores at segment level, essentially given the past context, try to predict the next segment. And that will be then passed into a peak detection algorithm, which will find the segment boundaries. And as other existing algorithm did, we also fine tune the peak prominence value on a validation test set. And to benchmark it, we use the Timit and Buckeye datasets, which are typically used for measuring the performance of segmentation algorithm. And for Timit, we use the standard train test split with 10% of the train data is randomly used for validation. And for Buckeye, we split the data into 80, 10, 10 for train test and validation. And for word segmentation, for more analysis and comparison with other systems, we also trained the word segmentation data on Zero Speech 2019 English dataset and tested it on Buckeye. This just shows how this model performs cross datasets, or it's generalizing across datasets or not when the language is the same. And how do we evaluate for both word segmentation and phone segmentation? We measure the performance with precision, recall, and F-score. And to measure all of these, we use a tolerance window of 20 milliseconds. And recall is defined as given a manual boundary, we will check if there's a boundary predicted within 20 milliseconds or not. And if there is, then you count that as a match. And if not, then you count it as a mismatch. And precision is defined as other way around. Given a predicted boundary, you check if there's a manual boundary within 20 milliseconds or not. And F-score is essentially the harmonic mean of recall and precision. It ensures that you're not predicting a lot of boundaries or very few boundaries to game the system. And then we have another metric, which is defined as R value, which focuses on over segmentation, how many times you are predicting extra boundaries. And these two, like F-score and R value, are typically used for measuring the performance of segmentation algorithm, and we use the same. And to not use just the best system or to normalize for different runs and different Cs, we report all the results with averages of 3 runs. So it kind of normalizes the variations if you will get with different seeds and different starting points. So now we look at the phone segmentation performance, and the most recent method that we are building on is the CPC-based system, which was the current state of the art. And if you look at the results comparison between CPC and SCPC, as you can see, we increase the phone segmentation performance, but the margin is not that much. But it does show that adding word information or a higher level segmental task does help learning even better frame level similarities. And one more line is, if you look at CPC plus, the CPC plus model is trained with extra data from Libre Speech. So SCPC is not only outperforming CPC, which is trained on same data, but it's also performing CPC when it's trained on a lot of data, 500 extra hours from Libre Speech. So it just shows that adding more constraints or looking at multiple hierarchies in speech signal can be really helpful in low resource scenarios. And as we do the same for word segmentation performance, and we compare this with a bunch of methods. And if you look at the top two, which is ESK means and BESGMM, these two are non-neural state-of-the-art methods for word segmentation performance, and SCPC outperforms both of them by a better margin than the current phone segmentation algorithms. And if you look at the next four, they are trying to do word segmentation by using a dynamic programming on top of the features that are generated from CPC. So that's a neural method, but we are significantly outperforming the other existing neural methods. So that means like the single model SCPC can do both phone segmentation and word segmentation, and is leveraging some extra information from both the tasks. And to verify that, we essentially did this experiment. If you look at the first row of this table, we trained two systems. One is trained with just the frame level loss, and other is trained with frame level loss and the segment level loss. And even for phone segmentation, when you add the segment level loss or the next segment classifier, the performance improves. And we do the similar task for word segmentation. When we train a word segmentation system which just uses the segment level loss and does not focus on the frame level loss, and we observe the similar thing when you add both frame level tasks and segment level tasks, the phone segmentation and word segmentation is performing. So that means they are getting something from different level of hierarchies to do better segmentation. So essentially adding segment level loss is improving phone segmentation, adding frame level loss is improving word segmentation. So these two are essentially trying to direct the model in a way which is beneficial for these two tasks. And we have done a bunch of ablation studies. This one shows how does the boundary threshold affects the final phone segmentation performance. So we trained 30 systems, 3 for each of the boundary threshold, and we vary the boundary threshold from 0 to 0.1 with the step size of 0.001. And as you can see, the model depends on the threshold, but the variation is very little. All the variations for at least phone segmentation can be summarized as 3% or 4% if you change the boundary threshold. So it's an important parameter, but it's not very, very critical that will break your system. And even in the worst case, it seems to be 85 something, and state of the art before SCPC was 86.02. So it's very, very close, and the trend seems to be similar for both Timid and Buckeye. And for word segmentation, it seems that the boundary threshold is affecting the performance more than the phone segmentation. And the trends are again similar for Timid and Buckeye. And another thing that you notice is for phone segmentation, the threshold or the optimal threshold seems to be a lower value, which is around 0.004. That's when the model does best phone segmentation on both Timid and Buckeye. And if you want to do word segmentation, the optimal threshold value seems to be higher. Its optimal is around 0.00775. So from that, what we are seeing is like when the model wants to do better phone segmentation, you work with a lower threshold. If you want to do word segmentation, then you work with a higher threshold. And our reasoning or our understanding is the number of phone segments is typically higher. So when you have a lower threshold, the model can generate more number of segments, which can match better with the higher number of phone segments. And if you want to do word segmentation, by using a higher threshold, the model will generate very few segments, which will be matching better with the lower number of word segments. And another is how do we add the next segment loss? Do we train the model from the very start by focusing on both NFC and NSC, or do we let the model train at frame level task for some time and then wait for it to train and then add the next segment loss? And we did the same experiments and we found out that waiting for some time seems to be helpful for both the tasks. And there's a very huge dip for word segmentation. One of the seeds performed really, really bad. So I will try to rerun it and then see if the seed is there or if there is something at third epoch that is really, really degrading the performance, or if it's just a random run that just happens to be really, really bad. But yeah, waiting for 1 or 2 epochs for the frame level model to train and then adding the segment level loss seems to be better for both the segment level or phone segmentation and word segmentation. And yeah, and this is this is our attempt to learn the boundary threshold. As you have seen from the previous experiment, the boundary threshold is an important parameter for the boundary detector, and our formulation allows the threshold to be learned simultaneously with the model, as you can backpropagate through the value of the threshold. So that's what we do. We essentially ask the model to train itself in such a way, itself with the value of threshold. And if you see, the model performs very, very similarly if you are trying to learn threshold or if you hand tune it. And for phone segmentation, the learn threshold seems to be a little lower below the hand tuning, but for word segmentation, it's slightly higher, like from 40.31 to 40.47. But overall, it just shows that it is possible to learn the threshold along with the model parameters. And when you try to do so, the model can come at a reasonable value. And it's essentially very, very close to the hand tuning of the fixed threshold. And there are more experiments that are related to the how we do learning threshold. But yeah, and this ablation study talks more about how does the segment representations affect the final phone segmentation, word segmentation performance. And if you remember, we were using average pool as an operation to generate the segment level representations or to sort of handle the variable number of frames within a segment. So we changed this to different poolings that people use, mainly we use maximum of all the frames within a segment as the final segment representation. And midpoint essentially refers to as the middle of the segment is used as the fixed dimensional representation. And weighted average is essentially a transformer like architecture to generate the average or to generate the weights, which are then multiplied with the frames within a segment, and then we take the weighted average. And for all these experiments, we found out that average and weighted average seems to be working really well. And the reason for that is max and mid. If you take mid, for example, even if you change your boundary by one frame, the mid representation will change, and average seems to be less sensitive or the least sensitive to the changes in the boundary detector. And to elaborate more on that, let's take three phones, for example. Phone A has the boundary at 0 and 2. The phone B, or the same phone in the next instance, has boundaries at 0 and 3. And in another instance, the same phone has boundaries at 0 and 1, and the minor boundary is at 2. Since we are using a boundary threshold, or sorry, a recall window of 20 milliseconds, all these will be classified as good boundary detections because they are within 20 milliseconds or 2 frames of an actual boundary. So from a boundary detection perspective, all these are very similar. But if you try to take the middle of these, they'll be very different. So the changes or the noise in the boundary detector changes the boundary segment representation most for middle, max, and average seems to be the least sensitive to that. So that is our reasoning. And we are trying to explore more into how do we generate this fixed dimensional segment representation by doing something like a transformer architecture on the frames, and then generate a like how transformers generate a representation for an entire sentence. Can we do something similar for a segment? And this is an analysis on 2, which shows how using PT1 and PT2 is better than just PT2. So essentially what we did is we trained 3 systems which use just PT1 to find the boundaries instead of using both. And we realized, or we saw that the PT1 is significantly worse than if you use both PT1 and PT2 for combining the evidence for boundary detection. And yeah, this is another ablation study which talks about how we can sample negative examples. If you sample the negative examples from same utterance or different utterances, and it has been a trend that same utterance seems to work better for phone classification, and mixed utterance seems to work better for speaker classification. And if in our task we're trying to do phone segmentation, so that is true. If you sample from same utterance, it works better if you than the mixed utterance. And the trend is similar for both Puck-I and Timid, and for both phone segmentation and word segmentation. And this is another ablation study that we did to see how does changing the context segregation network affects the final performance. If you remember, at frame level, we are just trying to predict from the previous frame instead of a context network. And at segment level, we're trying to predict from a GRU or a RNN. And we wanted to see how much performance will degrade if we, instead of a GRU or a RNN, we just try to predict the next segment from the previous segment. And it does degrade, but not as much as we had hoped for, or not hoped for, as we were originally expecting. And it does seem the improving the RNN part can improve the phone segmentation and word segmentation. And I've been working with changing the RNN to a transformer like network, or like a higher or more number of GRU layers to improve the context network. That seems to help performance a bit. And the last part was we tried to do the boundary segmentation analysis. And if you look at the figure, let's take these 2 phones, which are, let's take these 2 successive phones, which have a manual boundary, which is denoted by the the red line in the middle. And they have different classes. And we wanted to see how does the class labels of class A and B affect the boundary detection performance. And the aim of this was, is it easy to detect a boundary between a vowel and a fricative, as opposed to a vowel and a vowel, or a vowel and a semi-vowel. And to measure that, essentially, that's what we did. we took all the possible pairs of two consecutive phones, and we measured how many times the model is predicting a boundary within a 20 millisecond of the manual boundary. And then we made this huge table, which essentially tells us how easy or how difficult is it to predict a boundary between two different classes. And we found out that the boundary between a semi-vowel or a vowel followed by another semi-vowel or vowel are the most difficult. And you can look at the entire big table in the paper, but these were some of the lowest numbers that we saw. And the difficulty of segmenting two vowels or two semi-vowels that are following each other was same for both CPC segmentation and SCPC segmentation. So all the segmentation methods seem to be struggling with detecting a boundary between vowel and a vowel, or semi-vowel and a vowel. And the reason is the boundaries between two vowels is often very, very gradual. So the model has difficulties finding those boundaries. And if you look at the other numbers, for example, fricative followed by a vowel or fricative followed by a nasal, those numbers all seem to be in 80s or higher 90s, but vowel followed by a vowel seems to be as low as 40. So these are some of the boundaries that model has the most difficulties in identifying. And we are now seeing how can we use this information to improve the boundary detection, either in a two-step process or just do something within the model so that it focuses on a boundary between a vowel and a vowel better. And now we wanted to use SCPC for something more than just the segmentation process. How much time do I have? Oh, so I will just go through it really quickly so we have time for questions. So essentially, we saw SCPC can already generate the representations at segment level. And if you look at all the representation learning tasks, like even from handcrafted features such as MFCCs or CPCs or other, they use a fixed sampling rate. And by fixed sampling rate, I mean a feature is extracted every 10 milliseconds, and the number of features extracted from a speech signal just depends on the duration rather than the semantic content. And we wanted to use SCPC for sampling speech irregularly whenever there is a semantic content change rather than just the length. And that's what we did. And we directly took SCPC, we trained it, and we tried to measure the accuracy of the segment representations and frame representations on a linear phone classification task. And we saw that SCPC as it is does very, very poorly on phone classification. And then we went on to this deep analysis into what makes SCPC or CPC for segmentation different from CPC for representation learning. And we saw these three main differences. The CPC for segmentation has no frame level context network, which makes the task harder or easier for the model to learn. And CPC for segmentation was predicting, these are opposite. CPC for segmentation just predicts the next segment or next frame, whereas if you look at all the representation learning table, they predict much, much farther into the future. And in CPC for segmentation, we were trying to directly predict Z from the previous Z's. There was no regression layers, but in representation learning, we used one layer transformer as a regression layer. So then we changed the architecture of SCPC to the architecture of CPC for representation learning, and we still saw the same poor performance. And then we realized there's a trade-off when you try to do segmentation and classification by the same model. The left plot is R value on TIMIT. And what it's showing is if you predict farther into the future, the segmentation performance goes down, as the segmentation is essentially focusing on how different the very next frame is from the current one. So predicting much farther in the future doesn't seem to help the model learn the very fine differences between the current frame and the next frame. Versus if you look at the right table, which is based off on the data from the original CPC paper, they showed that if you predict much, much farther into the future, the representation learning will be better. And if you predict 12 steps into the future, the representation learning will capture the phone information the most. So now there's a trade-off. If you predict Farther into the future, the representations will capture the phone class information really, really well, but they will ignore the fine boundaries that exist between some classes and do poorly at phone segmentation. But if you just predict the next frame or next, then it can focus on very, very fine differences between the current frame and the next frame and do really, really well on phone segmentation tasks. But now if you're predicting very close to the future, the phone representation or the phone class information will suffer. So to avoid this, for now we just divided the task of representation learning segmentation in 2 steps. So we use a waveform, we pass it through a pre-trained CPC, which is focusing on essentially the learning phone class information, and then we pass those representations through ASCPC, which is dividing this into like variable number of segments, and then we can generate a segment level representation. And the SCPC still has a frame level encoder and the segment level encoder. And this is what we get. If you look at just the MFCCs, and this is the linear phone classification task on TIMIT, we extract 100 MFCCs per second, and these are they achieve around 47 accuracy on linear phone classification. And if you directly extract these features from a CPC that is trained for representation learning, it achieves much better phone accuracy performance, but the number of frames that you're extracting is still 100. And so what we did is we extracted the segment level representations from the SCPC, and we did the same task, and all the representation within a segment are repeated to match the number of frame level labels. And if you see, the performance is better than the MFCCs or significantly better than MFCCs, worse than the frame level representations. But what we have done is we have reduced the average sampling rate from 100 to as low as 14. And why it is useful? Suppose say we want to do some downstream task, say learn semantic word representation, which is a popular task on Zero Resource 2021 challenge. Now, if you were to work at frame level representations, you have to process all these 100, versus if you were working at the segment level representations to go something to word level, you now need much less compute to process the same amount of data. As you can think of this as it's reducing the amount of data that you need to process by a factor of 1/8. And another advantage that we saw of doing something like this is you can look much farther or much into the past, into the future. Now, say if you wanted to look 10 seconds into the future, you will have to look at 1,000 frames, and RNN or a transformer would have to process all 1,000 frames. But now if you want to look 10 seconds in the future at segment level, you just need to process around 90 frames. So it allows us to look much farther and into both back and past by working at segment level. And we also did extra experiments to see how does the quality of boundary affects these quality of the segment level representations. And we found out that the model is still missing or not doing as good as the metal boundaries for the representation learning task. And if you do that, the performance improves and the average sampling rate goes even down. So yeah, these are some of the conclusions that we have. And first one is essentially learning from multiple time scales is beneficial for unsupervised learning methods. And if you include auxiliary tasks that just don't look at frame level, but also look at higher phone level or word level, then they essentially perform better than just looking at frame level. And we also showed that phone segmentation and word segmentation can mutually benefit from each other. And there is a trade-off between CPC for segmentation and for representation learning. And this one might be just because the way we are doing segmentation might not be a universal trade-off. And if you use other segmentation techniques, which not just look at the disparity between the current frame and the next frame, you might not see something like this. And as for future work, I'm working on improving the boundary detector. As you can see from the last table, improving it automatically improves both the word segmentation and the sampling task. And we are also looking into how we can focus on the boundaries between two successive vowels or semi-vowels, and how do we make the model do better on those boundaries. Yeah, thank you. Sorry for rushing in the end. If you have questions, please let me know.
Thank you very much. for the very dense and great talk.
Yeah, sorry.
No worries. I mean, if people have questions, feel free to unmute yourself and just ask. And if you can't do that, you can also put the questions in the chat. All right, I guess I'll start.
Okay.
Have you actually tried training the segmental part alone without even training the frame CPC loss?
Yeah, that's what we did here. Yeah, in this, we trained the segment level model directly without using any frame level loss. And it didn't work as well as if you train it with the frame level loss.
Right, because I suspect if the model starts with a really bad, say, segmentation, it will just stuck there without improving the segmentation.
Yeah, but the thing is, like, it's not as worse as I expected it to be. It can still learn the fault boundaries or phone information somehow, if even if it just asks you to predict this next segment from the previous segment. And the reason is it's sort of doing a language modeling at phone level, and if you have very poor boundaries, it won't be able to do the phone level language modeling task. So it has to do some sort of like accurate or close to accurate boundary detection.
Right, and it seems like there is no loss to encourage a better segmentation, I guess. Have you thought about, marginalizing the boundaries instead of just using a binary ones?
So yeah, so there is no direct incentive for looking at better or try to improve the better boundaries, but it sort of is an indirect way. If you do not do better boundary detection, your segments are gonna be all over the place, and then you're not gonna be able to do the segment level language modeling task really well. So that's the only motivation for the model there is to do better boundary detection. And yeah, I mean, there are parts of it that can definitely be improved. For example, we are using a like straight through trick, and now I have a model which does not require a straight through trick. And this is one thing. And can we just try to predict much farther into the segment while keeping the frame level loss just to predict the next frame? And how does that affect the segmentation and the representation learning performance?
All right, thank you.
Yeah.
Question?
Hi, thank you
Hey.
for the talk. Since you're on the slide, I had a clarifying question.
Mhm.
So the frames are first downsampled, right, to get the Z representations. So I was wondering if they're downsampled, how are the boundary markers determined? So are they based on the last frame of that convolution operation downsampling, or how were you deciding that?
Yeah, so the boundary detectors are essentially based on the last downsampling layer. Now these are our features. So the level that the boundary detector and the Z are operating are essentially same. The sampling rate of both of them are same. And you could, in theory, just directly start from MFCCs and nothing will change.
Thank you.
Yeah.
Hugo, you are on mute.
Yeah. Thank you for your talk. I have a question about the loss function you're using. I didn't write
Sure.
down the slide number. Yeah.
This is the frame level loss.
Yeah. So I see you're using a cosine distance between the Z. So, well, there's two things. First thing is that cosine distance is not sensitive to the length of your Z vectors. is that intentional? And secondly, the cosine similarity is between +1 and -1. So which means that your exponential is going to be between 2.7 and 1/2.7. So that's kind of limiting how sure the model can be about the similarity of these two vectors. Is that also intentional? And is there a temperature parameter that you could play with there?
Yeah, so I will answer the second one first. Yeah, there is a temperature parameter that you can play with in the learning process. I will include it here. And I didn't quite understand the first question.
Well,
Like cosine similarity is not in like, but these are the ZT and ZT plus 1 are of same length. So there is nothing like length.
Oh, they are
you mean the
normalized.
dimension of these to Z?
No. I just mean that the length, the L2 norm of the Zs, if that changes, it will not change your loss function. So, but maybe your Z, they are normalized anyway. Okay. Is that what you're saying?
Yeah. So they're normalized anyway, so that does not matter. And we did try to work with unnormalized one. This seemed to work best based on our work and the previous work that used CPC for segmentation. And there are some of these hyperparameters that I don't have a really good explanation for. They just worked really well.
Okay, thank you.
Yeah. But yeah, I mean, now I'm looking into like sort of using a regression layer instead of just the cosine network, cosine similarity to get the similarities.
There's another question in the chat. Sorry, Ramon, what were you going to say something?
Yeah. I had a question also.
Go ahead.
Thanks for the great talk. Did you try to experiment with ground truth phonetic boundaries for the?
Yes. For word segmentation, I don't think I have the results here. And we did try to do that, at least one experiment that I have here. Like if you look at just this experiment where we are trying to do the phone classification or linear phone classification from the segment level representations, we can see the metal boundaries are increasing the performance by quite a good margin. And so that means there's still an area where we can improve the boundary detector, and then it can perform as good as the metal boundary detector. And I think it might not be just the issue of predicting good boundaries. It might be dependent on how consistently we predict the boundaries at the same location so that the segment level representations are not different each time.
Okay, great. Thank you. Thank you for the talk.
Yeah, and the word segmentation performance is slightly better if you use the metal boundaries instead of the boundaries that you directly get from the differential boundary detector. But then that makes the entire model like some kind of supervised, not unsupervised. So.
So is this for, you have like from 58 to 62, no? That is the difference.
Yeah. Okay. Yeah, that is the difference.
Great. Thank you.
Yeah.
Okay.
And the number of segments seems to be also smaller. That reduces the average sampling rate. And there's a question in the chat. Okay.
Right. So there's a question in the chat. I'll just repeat it. We'd like to know what's the reason for the trade-off between phone classification and segmentation. They seem to be somehow correlated. Yeah, maybe you can elaborate on this trade-off. I also feel like it's kind of weird.
Yeah, so they are related. In theory, if you were to do like really good classification, or if you could capture the phone classes really well, then you could do segmentation. The reason for this trade-off is the way the SCPC or our model is trying to do segmentation. To do segmentation, if you remember, we are making a vector of similarities or dissimilarities between the current frame and the next frame. So if you could capture the very subtle differences between the next frame and the current frame, then you will be doing very, very well with the phone segmentation task. But for representation learning, you sort of want to predict further into the future, so your model is constrained, and the task of identifying the next frame is not trivial for the model, so it can capture the better phone classification, as I mentioned. So this is why we think the trade-off between the two is happening. And it might not happen if you use a different boundary detector, which just looks at more data points instead of just the current one and the next one.
I see.
So
So
yeah. So it might be partly due to the way we are doing the segmentation, not because there is a trade-off or like always between the two tasks.
okay. So if I need to interpret this, would it be fair to say that you want to preserve, sharp spectral changes in the representation in order to get
Yeah.
accurate segmentation, but then that's sort of hurts the segment representation when you do averaging.
Yeah. And another is if you want to do really good segmentation, what can't happen is you can't suddenly change the phone class in between. So that'll introduce an extra boundary. But if you're trying to do, say, phone accuracy, even if within a segment you misclassified one frame, that doesn't matter. The phone accuracy is still very, very high. But if you just miss one frame within a segment, that is introducing another boundary. And that is why your boundary performance is really dependent on how well you can predict the next segment consistently. Within a segment, you're not allowed to make any mistakes in predicting the next one. So that's why it makes more sense to focus on just predicting the next segment and even capture the very small or very subtle differences in the boundaries.
Yeah, and I guess that also explains why this model finds semi-vowels and vowels, transition between these two things hard because there are no
Because this is
sharp-
very, very
yeah.
gradual. Yeah. And they had both, like if you look at vowel versus vowel, they both have really high energies, and then the model sort of thinks they're both in the same class. And yeah, I mean, maybe next time I'll include a figure. Even in the best case scenarios, the boundaries that the model seems to be missing is when you have two vowels that are just occurring together and there's a very smooth transition between the two. So yeah, so this is essentially a combination of like the way we are doing things and then the way phone accuracy is evaluated at frame level. So I'll just repeat it. Even if you miss one frame, the phone accuracy is not going to be impacted that much. But if you miss or insert an extra boundary within phone segmentation, then you will have extra boundary that will impact your boundary detection or segmentation performance way more than. So yeah, that's the reason, at least as per our understanding, for the trade-off between the segmentation and accuracy, like linear phone classification accuracy.
Okay. Any more questions? Well, I guess we're way over time anyways. So thank you, Saurabh, again for the great talk and for answering all of these questions. I think this is just fascinating. So thank you for the talk, and thanks everyone for attending the talk. This is going to be the last talk of this year, and then hopefully I'll be able to do something else for the next year as well. So stay tuned, and I'll see you some other time. Bye. Thanks, guys.
Yeah, thank you for inviting me. Yeah, someone asked, can we get the slides? I can try to upload the slides.
Yeah, you can just send it to me, and then I'll put it on the website.
Okay. Yeah. Thank you for inviting me, and thanks everyone for listening to the talk. Have a good day.
All right. See you guys.